All right, let's talk about a bacterium that's having a bit of an identity crisis. Atlantibacter hermonnii, or as many of you probably still know it, Escherichia hermannii. Just a quick heads up before we jump in. Everything we're about to cover is pulled together from a Gemini deep search. If you want to dig into the original sources yourself, all the citations are right there in the linked notebook for you. So, right off the bat, what are we even supposed to call this thing? Believe it or not, this isn't just some academic debate. It's a real question that has direct consequences for us in the clinical lab every day. So here's our game plan for this briefing. We'll start with that naming conundrum, then move to the lab bench, see what it actually does to patients, figure out how we treat it, and finally, how to stop it in its tracks. Okay, first up, a tale of two names. Let's really get into this taxonomic tussle, because it's a fantastic look at how modern microbiology is evolving right before our eyes. So picture this, for over 30 years, since 1982, everybody knew this organism as Escherichia hermannii. The classification was based on the best tech at the time. But then, fast forward to 2016, researchers used much more powerful genomic tools and realized, wait a minute, genetically this thing is way out on its own branch. It's not really an Escherichia. And that's when they proposed the new genus Atlantibacter. And, well, that's where our story gets interesting. And that brings us to today, where we're basically living with a dual identity. If you look in the big genomic databases like NCBI, you'll see Atlantibacter hermannii. That's the most up-to-date name, genetically speaking. But a lot of clinical bodies are saying, whoa, hold on, let's stick with Escherichia hermannii for now, to avoid confusion. So the bottom line for us, you absolutely have to know both names. All right, let's head over to the bench. How do we actually spot this character when it shows up on a plate? Okay, the first thing that should make your microbiologist senses tingle is this. That beautiful, bright yellow pigment. It's a dead giveaway. You'll see it on media like blood agar, and it's non-diffusible, meaning it stays right there in the colony. So let's run down the basics. Under the scope, no surprises. It's a gram-negative bacillus, it's motile, zipping around with its Paratrichus flagella. It's a facultative anaerobe, so it's not picky about oxygen. And on the culture plates, we've got that yellow pigment on blood agar, and on McConkey, it's a lactose fermenter, so you're going to see those classic pink colonies. But how do you really nail the ID and separate it from its famous cousin, E. coli? Well, besides that yellow pigment, there are a few key biochemicals. It's positive for cellulose fermentation. That's a big one. It also grows in casein broth, something E. coli can't do, and it's typically indole positive. It's this specific pattern that really helps you lock in the identification. Here's a really neat trick this bug has up its sleeve, and it's super useful for us. It has a chromosomally encoded beta-lactamase called HER1. This means a true wild-type Atlantibacter hermannii is always resistant to drugs like ampicillin and amoxicillin. It acts like a free quality control check. If you get an isolate you think is Hermannii, but it tests susceptible to ampicillin, you gotta go back and double-check your ID. Okay, so we found it, we've named it twice, but what's the big deal? What does it actually do when it gets into a patient? Now, this is super important to understand. Atlantibacter hermannii isn't some hyper-aggressive pathogen. It has pretty low intrinsic virulence. It's not going to make a healthy person sick. No, this is a classic opportunist. It waits for a weakness, a compromised immune system, a break in the skin. And its number one weapon is its ability to form biofilms. It loves to set up shop on medical devices. And if you look at the types of infections it causes, this strategy becomes crystal clear. The overwhelming majority, we're talking over half of the cases, are bacteremia or sepsis, and they're almost always linked to a catheter. It also pops up in wound infections, some UTIs, and even osteomyelitis, but that bloodstream infection connection is really its claim to fame. This brings us to a critical take-home message. When you find Atlantibacter hermannii, especially in a blood culture, you can't just write it off as a contaminant. It is a clinically significant finding. It's a huge red flag pointing directly at a device-associated infection. Your first thought should be, where is the plastic in this patient? So we have an infection. Time for the counterattack. How do we treat it? And what kind of resistance are we likely to face? Okay, we already know it's naturally resistant to ampicillin. That's baseline. But the real threat is what it can pick up from other bacteria. We're seeing strains that have acquired genes for ESBL production, think CTXM and SHV types. And even more concerning, there are reports of strains producing carbopenomases like NDM and VIM. This is how a relatively low virulence bug can suddenly become a multi-drug resistant nightmare. So when it's time for susceptibility testing, this is key. There are no specific breakpoints for Atlantibacter Hermannii. You have to use the established EU-CAST breakpoints for the whole Enterobacterellus group. So you'll be looking at the standard breakpoints for drugs like piperacillin tazobactam, ceftazidime, and meropenem. And for treatment, if we look at guidelines like these from the Dutch SWAB, they point us towards standard Enterobacterellus therapies. For something like urosepsis, maybe cefuroxime or ceftriaxone. But notice the duration often depends on one crucial factor: source control. You can give all the antibiotics you want, but if that infected catheter is still in, you're fighting a losing battle. Now, what about kids? The general principles are the same, but there are a few important differences. First, of course, all dosing is weight-based. Second, we generally try to avoid certain classes of antibiotics, like fluoroquinolones. And for serious ESBL infections, meropenem is often the go-to drug, just like in adults. All right, last section. The best treatment is always prevention, right? So how do we stop these infections before they even start? It really all comes down to the fundamentals of infection prevention and control. There's no magic bullet here. It's about meticulous hand hygiene. It's about using contact precautions for any patient with a known multi-drug resistant strain. And most of all, given its love for biofilms, it's about absolutely strict aseptic technique when inserting and caring for any kind of medical device. That's where we can make the biggest impact. So this brings us to the big question for your facility. Is Atlantibacteria hermannii the next emerging threat you need to be watching for? With its knack for forming biofilms and its potential to pick up nasty resistance genes, it's definitely an organism that should be on our radar. And that's our deep dive on Atlantibacterium hermannii. If you found this useful, definitely subscribe for more briefings like this one. And we really want to hear from you. What's your experience been with this organism? Have you seen it in your lab? Let us know in the comments below. We'd love to get a conversation going.